In this example here, we can see how we can apply roots and powers when there's multiplication, but we cannot apply roots and powers when there's addition and subtraction. So here, if I try to square root parts of this, I'm not allowed to do that. However, if I factor and express this with multiplication, then I would be able to apply some square roots to this. So the first thing I'm going to do here is I'm going to factor out the greatest common factor. So the greatest common factor is going to be 16a4b. Then times. Because I have now a times here, this is going to allow me to apply the square root. What's left over though is I have to make sure what's left over. So 2 plus 3ab. So there's nothing in here I can do because I can't square root any of that because there's a plus in there. However, there's a times in between here. So if I want, I can now express the square root of the times part separately. And then I can square root this part. So we end up with 4a. Oops, this cannot be square rooted, so I'm going to leave that in the square root portion. So I'll pull the perfect square out of there. And it's going to be b2 plus 3ab. And so that can be square rooted. This can't, so it's going to be left as b times 2 plus 3ab. For f it's the opposite. If we're going to put this into the radical, we need to first of all multiply it in. We have to first square it to get it inside the radical. So a 6 c squared, and then we can apply the multiplication across the plus with distributive property. And so we end up with the square root of 12a7 b cubed c squared plus 16a9 b7 c squared. Okay, looking at this problem here, this is called an exponential growth problem. So when we have exponential growth, the way that this works is a population of mice is doubling every month. If it starts with 30 mice, write the expressions to show the exponential growth. So in general, the exponential growth equation looks like this. The end amount is equal to the start times the growth factor. So in this case, we're starting with 30. We're doubling, so our growth factor is 2. And it is to the number of, the power represents the number of growth cycles, or the number of times we multiply by the growth factor. In this case, it would be 2. So it's doubling every month, so that's our growth factor. The number of months represents the growth cycle. And so my equation looks like this. So for part A, the end amount is equal to the starting amount of 30. Okay, maybe I will just highlight these pieces. So the starting amount is 30. My growth factor, my growth factor is going to be times 2. So it's doubling. And the number of growth cycles is going to be our unknown. So we'll call that x. So that's how many growth cycles that we're going to go through. So this is a function that calculates the end population after x number of months. So then for this problem here, how many mice are there after 1 year? So we're going to do the end is equal to 30 times 2 and to the power 12. And this becomes a really big number. So you can just type that into your calculator and work out that value.